Welcome to Essential Problems with Crit. We continue focusing on Lewis structures. We're going to focus in particular on drawing polyatomic ions. Let's begin with carbonate. Nice place to begin. So carbonate, of course, you should know your polyatomic ions. They should be rationalized and memorized. So we have CO3 2 minus, and the first thing that we're going to do is count the total valence electrons. Carbon has 4 valence electrons. Oxygen has 6. 6 times 3, 18. 18 plus 4, 22. And there's a 2 minus charge. So 22 plus that 2 extra electrons that entire structure has gained, we have 24 valence electrons. This is a very simple thing to do. A lot of students skip this step. However, it's a really important check. It will make sure that you don't do a kind of very, simple mistake that destroys the structure. Let's begin by placing our atoms. And typically with polyatomic ions, that first element will be placed in the center. So unless otherwise noted, that will be placed in the center. Let's place our oxygen atoms around it, placing them kind of equally dispersed. And of course, if you know a bit about Vesper theory and maybe about how the structure will look in the future, that's why you can see why I'm drawing that. It's okay to mess up initially drawing it. You can always correct it later. So don't try to approximate. We can fix it later. So now the first thing that we're going to do here is actually place our covalent bonds. Now, these are nonmetals, so therefore they're not going to experience an ionic attraction between them. They will have this sharing that will occur, and we're going to represent that sharing of valence electrons using a line, right? So if I draw that oxygen is sharing 1 electron with carbon, and carbon is sharing 1 electron with oxygen. And we can go ahead and draw those covalent bonds around carbon. And right now, I've placed 6 electrons on this structure because each bond represents 2 electrons being shared, 2 valence electrons being shared, one by one of the atom and the other by the other atom. And essentially, their orbitals are overlapping in completing their mutual attraction. So now I need to place my other electrons because I've placed 6, right? And so that means I have 18 electrons that still need to be placed in the structure. Well, now I'm going to use unshared pairs. And I'm going to place the unshared pairs in the effort to complete, right, our valence. And so for oxygen, we should have 8 electrons total around this structure. We can't go beyond that for the second energy elements. So everything in the second energy level, right, can only fit a maximum of 8 electrons. So we should kind of put some rules here, right? So hydrogen and helium can only fit 2 electrons, right? That should be intuitive because that's the first energy level. All the second energy level elements can only fit a maximum of 8. But there's some exceptions to this. So like you will encounter boron, right? Actually, let's put beryllium first because beryllium comes first on the periodic table. Beryllium can only fit 4 electrons around it. So it's kind of an exception. Boron can only fit 6 electrons around it. And then carbon, nitrogen, oxygen, fluorine, neon, so all the rest can only fit 8 electrons. Any other element can have an expanded octet because they have larger energy levels. And so they will typically have 8, but you can fit more electrons around it. So that's important to note. So let's go ahead and complete the oxygen atoms here with unshared pairs. And I'm going to complete the more electronegative first. That's always a good thing to do because electronegative means that they're going to draw electrons to it. So here I'm placing, notice 1, 2, 3 unshared pairs around this oxygen so that there's a total of 8 electrons surrounding oxygen, right? There's 2, 4, 6, 8, right? So again, total around it. And that's now that oxygen is complete, if you will, right? And so we can do the same thing with that oxygen and that one as well. Now, if you look carefully, we have placed all 24 of our valence electrons. We've got 2, 4, 6, right? 8, 10, 12, 14, 16, 18, 20, 22, 24. So what do we do at this point? At this point, we should place formal charges. So after you've placed your total electrons, you should definitely move to placing charges. And so just like we did with the ionic crystal, right? We need to look at how many electrons are directly on each atom, okay? And if we're looking at oxygen, right now we've got 1, 2, 3, 4, 5, 6, 7 electrons directly on that atom. If you see, yes, it is completed by sharing, by this mutual sharing, but if we're just looking at that oxygen atom, right, there's only 2, 4, 6, 7. We're not counting this because that's being shared from carbon. We're looking at just what is directly on the oxygen. And there are 7 electrons directly on that oxygen atom. So we're going to give that a negative charge because looking at the periodic table, oxygen should have only 6 directly on it. But in this case, there are 7 directly on it. So we're giving that a negative charge. We're assigning it a negative charge. This one as well. And this one as well. So right now we have these 3 negative charges. What's the charge of the central carbon? If we're looking at it, there are only 1, 2, 3 electrons directly on that carbon. So you could say it quote unquote lost 1, at least as far as how we're drawing the structure. So we need to place a positive charge on this carbon. So now that we've done that, we can already see this doesn't look quite right. And the reason why it doesn't look quite right is because carbon is not really complete. Right now you just have 2, 4, 6 electrons around the carbon, surrounding the carbon. So we really need to form another bond. And this is when what we use to do this is called pi bonding. And it's very important to note that pi bonds can move. Sigma bonds cannot move. The first bond in our structure, the first covalent bond that's always there is a sigma bond. If that were to move, the substance would be broken. The structure would be broken. So we can't move sigma bonds. And that's why it's important to follow this kind of method when drawing Lewis structures, because it helps to accurately represent how the structure will behave, right? Not just going ahead and drawing pi bonds wherever we want to place them. That's not a good technique because pi bonds are the things that can move, right? They're not the same. And so, not the same as sigma bonds. So how are we going to move them? We're going to move always an unshared pair, right, to form a pi bond. And you always do it from where there's a greater electron density to where there's less. So greater electron density is really on any one of these oxygen atoms. And so I can show the movement of these 2 electrons. Notice now I'm doing a double barbed arrow because I'm showing the movement of these 2 electrons to form a pi bond. And so we then draw the result, which would be carbon here. Again, everything else is the same. And then we've got this double bonded oxygen. Of course, I can only draw 2 unshared pairs on that oxygen now because that one unshared pair has moved to become a pi bond. Of course, this is not the only structure that I can use to represent carbonate ion. It is the first complete one. This one was not. This is kind of my sketch work. And notice I put this kind of one directional arrow here to show my sketch work. But this really is the first complete Lewis structure, right? But this is not the only one that we can use to represent. And it's actually technically not appropriate to just say that's it. Because the truth is that there are other equally relevant possibilities. So this is called arrow pushing. What I'm doing here is to represent how this unshared pair, or really any one of these unshared pairs on this oxygen, can move to form a pi bond, and here the pi bond can move back to that oxygen. Okay, and so now I can draw this other structure, but notice what I'm doing here. I'm drawing this arrow that's showing an equivalence. Okay, in drawing this other structure here, I have the pi bond, but now I'm going to have to draw this oxygen with a single bond and negative charge, as well as that other one there. And many times you'll see this kind of bracketed. Bracket's a little weird there, but that's okay. So notice we're indicating that this is equally able to represent as this structure. And of course, we can draw one more. And notice I'm drawing that to illustrate, again, this is resonating, meaning all of these structures, and really this is what the truth is, all of these structures are actually occurring all at the same time. You say, how is that possible? Well, recall that the whole point of those lessons, those early lessons where we discussed the behavior of electrons. Electrons behave as waves. And so you really can't accurately represent or understand what's happening here if you're not thinking of them as waves. Each of these structures are actually occurring all at the same time. And so these are 3 resonance structures for carbonate ion. Now, of course, will you always have to draw all 3 in all of the drawings that we're doing? No. But it is incredibly important to understand the significance of this. If you don't understand the significance of this, then it's very problematic. And honestly, we could draw one structure that would represent an average of these. Now, this is called the resonance hybrid. It's not typically drawn because you can't use it to draw use it in a reaction mechanism. But it's nice to kind of show the average of these. So what would be the average of these? If we could draw it over here, let's just for sake of comparison. So the average, if you will, quote unquote, would be everything that is the same, that stays the same. Let's just represent that. So what stays the same in all of these structures? Well, there's always a carbon atom in the center. And there's always these single bonds, this sigma bond, and there's always oxygens here. Right? And what doesn't change? There's always 2 unshared pairs on each of those oxygens. Well, what's changing? The pi bond. And so I can represent that by dashed lines. Okay? And then what else is not changing? Well, the charge of carbon is constant, right, in each scenario, but the oxygen's charge is changing. And so we can kind of represent this average by taking the total charge of oxygen on all of those 3, right? So that's 2 negative. And we can divide it by the oxygens that charge is distributed. So that would be 2 negative over 3, right? 2 over 3, 2 over 3. So each of those oxygens would have this kind of partial charge of 2/3 negative, right? Now, again, this is called a resonance hybrid. It's not what I want you to be drawing when we're working with our structures, but you should be familiar with it. It should make sense as this kind of easy representation. And really, this is the reality of the situation, because a pi bond will actually be smaller, right, than a sigma bond. And so the truth is not that, we're going from here to here to here, and then to here, and back over and over again. But all of these are happening all at the same time. And how do we know that? Because we can measure the distance of the carbon and oxygen in the structure, and we find that experimentally that they're all the same size. And so if they're all the same size, really all 3 of these structures are occurring all at the same time. However, at the same time, we will need good Lewis structures, and honestly, one of these can, as long as we understand the theory, can be more than adequate for representing the structure. Till next time,